here again at IMPA. Thank you all for giving me this chance to come again and visit and see some old friends that I hadn't seen for quite some time, and to see friends that I see on a more regular basis. It's a great pleasure. Thank you. So I'll try to tell you what we've learned working with a group of engineers at the University of Wyoming who did a lot of experiments to measure the hysteretic effects on the relative permeability functions in this system involving supercritical CO2 and brine. I guess the motivation is that sometime, I don't know if this is still is going to happen there, but they were seriously considering injecting CO2 in the subsurface in aquifers. There are lots of aquifers available in Wyoming. It's a huge state. It's essentially empty. The population is 500,000. But despite this fact, it emits a lot of CO2 by burning coal. So there was this idea of injecting CO2 there, and this sort of motivated this study. And so this is joined with the colleagues from the engineering department, Dan Marchesin, and Rahul, who at the time was a postdoc there at Wyoming and has now moved on. So this, as I mentioned, the idea is to, the focus is on CO2 sequestration by injection into aquifers. There are many possibilities for geologic formations that could accept some CO2 and possibly keep it down there, but saline aquifers are quite abundant, and so they provide a lot of room for CO2 sequestration. So this investigation is related to that, is in the sequestration in aquifers. And of course, the idea is to inject the CO2 there and hopefully to stay underground and will not leak back to the atmosphere. But it's a buoyant fluid, so it will rise. And unless there is some way to keep it there, it will come back to the atmosphere. So, sorry. So the major concern is whether it will be there or not. Of course, ideally, you should have an impermeable cap rock to keep it there, but due to injection, you may overpressurize it and open up existing cracks, and it may leak. And if you're planning to inject it in old reservoirs, there are also the possibilities of abandoned wells that provide a path to back to the atmosphere. So given that, there should be a way of, or some mechanism that keep the CO2 there in the short term. And one of them, which has been proposed in the literature, is capillary trapping, which is CO2 usually is the non-wetting phase. And so after you inject it, you're doing the drainage process, but then when water comes back in, or brine comes back in this imbibition process, so the CO2 phase will disconnect and give rise to ganglia and isolated bubbles that are effectively immobile. And so this is this mechanism that together with this impermeable cap rock provides sort of a short-term sequestration. And then there are also other processes like a solution trap in which the CO2 dissolves into brine, and then the mixture becomes heavier and then forms convective currents, and then it sinks the CO2. And by doing so, in the dissolution, the brine becomes acidic, and then enhance the chance of reacting with the rock, and the carbon will precipitate as a mineral. But those are believed to occur in a much longer time scale, so those two are sort of a short-term mechanism for confinement. So what my colleagues in Wyoming did was to focus on this mechanism for capillary trapping. As I mentioned, they measured using very sophisticated new labs that they built there to measure the hysteresis effects in the relative permeabilities. And we worked with them, and we learned a lot from their work, and this is what I will try to describe. So in this talk, what I do, I'll present the mathematical model, which is based entirely on the experiments performed by the colleagues, and then we'll use this very simple mathematical model to sort of analyze this mechanism of CO2 trapping due to imbibition, and this process can be sped up by the injection of a chase brine. So after injecting CO2, you inject a little bit of brine and to speed up the immobilization of CO2 as a residual phase. And then I'll show you some numerical simulations that double check this analysis. So the model is, as I said, is quite simple. It's based on several simplifications, and the main ones are here. So it's a two-phase model. So the wetting phase is a brine-rich phase. I will all the time refer to it as the water phase. And there is supercritical CO2, so these aquifers are quite deep. So at that depth, the CO2 is a supercritical fluid, and it's the non-wetting phase. And as in the experiments, the fluids were equilibrated to eliminate or to minimize the mass exchange. So our model reflects that. So we assume that there is no mass exchange between phases. And we also consider the case in which we are neglecting compressibility as well as capillary-induced diffusion. So this is the sort of the flow regime that we are dealing with. It's quite simple, but we've learned something out of that. So here, just to set up terminology, so these are the conservation mass for the brine. Again, I will always call brine as the water, and for CO2. So again, this study is one-dimensional, and we have a source terms because you'll be injecting water as well as CO2. So conservation of mass together with Darcy's law, and we take into account gravity. So like in the experiments, they were performed with a vertical core. So a cosine of theta in our case would be a -1. So the gravity points in the opposite direction of the positive x-axis in this analysis. So we have the saturations, the source terms, the absolute permeability, the relative permeabilities, which again were measured experimentally, the fluid viscosities and densities. So all of those parameters were measured, and they try to mimic the situation in this particular aquifer where this injection is supposed to take place. And porosity, so everything comes from that aquifer. So these are the equations, and we rewrite them in this more usual way in which we have one equation for the conservation of mass. I've dropped the subscript W here. From now on, S will denote saturation of water. So this is the mass conservation of water, and this is the total mass conservation. V is the total Darcy velocity, and the flux function of water is here expressed in terms of the fractional flow function, again in terms of the relative permeability functions and the viscosities, and this buoyance coefficient, or this buoyance term, which takes into account the gravity. Here I have already set cosine of theta to be -1, so the experiments were performed in this vertical direction with injection from the bottom. And E is the interstitial velocity, so it's the total velocity divided by porosity. So these are the equations. And to supplement this model, we need the permeability functions. And here they are. the symbols or the measurements on the left is the relative permeability of the CO2 as a function of water saturation. And on the right, the symbols are the corresponding relative permeabilities of water. So those are the conditions of the experiments, mimicking again the conditions at this reservoir. And the experiments were conducted at this regime where at the pore level, the capillary forces dominate the viscous force. So it's a capillary dominated regime at the pore level. And what they did was several cycles of drainage and imbibition to measure the effects of hysteresis on the relative permeabilities. And the curves here are there fit just to facilitate the visualization of the data. On the right side, the curve fits are our own fits, and where we use them to construct the model for the permeability, for the relative permeability functions. So I will explain them better in the next slide. But in addition to those several experiments of drainage imbibition to measure the scanning and relative permeability curves, they also did several unsteady state experiments just to measure the influence of the initial CO2 saturation in the residual, the corresponding residual one. So this is what you see here on this side. This is a graph of, again, the symbols are their experiments. This is the initial CO2 saturation at the beginning of the imbibition cycle. So that you're doing a drainage, and then at some point, when you achieve a certain CO2 saturation, then you reverse to a drainage, and then you measure the corresponding saturation at which the CO2 becomes immobile. So this is this map that maps the initial CO2 saturation to the trapped CO2 saturation. And those are the drainage measurements of a relative permeability. In blue, again, is the CO2, and in red is the water drainage permeability. And this green curve on top is the water permeability when the CO2 is immobile. So for each one of those dots, let's say when you have a CO2 immobile, the corresponding water permeability is given by that green curve. So what we did then was to we used those curves together with this data to construct our scanning curves. So the scanning curves use only this data. So the one point is the saturation at the top of a scanning curve, and the other point, the other coordinate of a point is the saturation at the bottom of the scanning curve. And we interpolated, so in the case of CO2, the drainage curve with the immobile curve, which is the horizontal axis, and in the case of water, is interpolated between those two curves using straight lines. So here are the relative permeability functions. So this is this fit. I here refers to the initial CO2 saturation, and S sub I is the corresponding trapped CO2 saturation. So using this, which we fit this way, we interpolated linearly to construct the relative permeabilities, and this is our model. So again, what you see here is the drainage, CO2, and water permeability. The top curve here is the green one. That's the permeability of water when the CO2 is immobile, and the straight lines are the scannings, which, as I said, were interpolated linearly using this simple model. Okay, so here we have the drainage, and these are the scanning curves, and this is their data just for comparison, using their own interpolations there. So this completes the model. So we have the simple equations of conservation of mass, and those are the constitutive functions that we use. So in terms of the flux function, this is how the flux function of water looks like. The solid curve is the drainage. this arrow should be pointed in the other way around because this can be used only for the water saturation decreasing, so it's incorrectly pointed. And the dashed lines are the corresponding scanning curves. And in this simple model, we assume them to be reversible, so you can go either way along the scanning lines. So these are, again, the fluxes, here expanded in terms of the relative permeability functions. And those were constructed with those parameters, so that's the realistic viscosity ratio for the fluids in place. And we assumed a sort of a background flow, and this constant value nu here reflects this existing background flow. And this is the buoyancy coefficient, so gravity is almost negligible relative to the other forces here. So then again, this is just equations, and so this immobilization process consists of two parts. The first one is the injection of CO2. And so during this time, what we have is drainage. And in a snapshot, what you see is that this gives rise to a typical Buckley-Leverett profile, in which you have a rarefaction wave and a shock wave moving ahead of it during the injection. And then at some point, you, again, to speed up this immobilization, you stop injecting CO2, and then you inject some brine. When you do that, you switch to imbibition. And to tell you what happens, I mean, this is essentially the most relevant thing that we've learned is that in doing that, immediately you form a trapping shock, so a shock wave that is peculiar in the sense that it has an extremely small amplitude in some cases, but propagates very fast. So it sweeps across this CO2 plume, immobilizing it almost instantaneously. So just to give you some details of this analysis, I hope I don't bore you too much with that, but you can essentially figure it out by looking at conservation of mass at the inlet. So in the injection cycle, you're not injecting water, you're just injecting CO2 initially. And through the injection, you change the speed or the velocity of the background flow ahead of the injection by this much. And if you look at the equations of conservation of mass at the inlet location, you obtain this relation where you're doing the drainage, so you use the drainage fluxes, and this conditions on the left is known because that is the incoming flow. And then with the injection and you're injecting pure CO2, you can figure out what is the saturation just ahead of the inlet, which is S+. And by resolving or solving those equations or re-expressing those equations in this form, that gives a relation between the injection rate and the parameters and the saturation just ahead of the inlet. For instance, in this case, and all the simulations and the results that I will show refer to this case in which this is the injection rate. So it gives rise to a saturation ahead of 0.6. So that is, again, water saturation just on top of the inlet during the CO2 injection. So then you switch to water injection. So you turn off the CO2 injection and switch to water. And again, you apply the same balance, but now it's easier if you look at the conservation of CO2, since there is no CO2 coming in. And then, but you have changed the history of the flow because you had been injecting CO2. So the flux on the top part of the inlet had experienced a change in saturation from 1 to S+ during the water injection. So now hysteresis kicks in, and so the value of S* that you get to preserve this balance, this flux balance, is the saturation of the water that corresponds to the immobile CO2 when the initial water saturation was S+. Since there is no flux of CO2 from the left, so this is 0, the right has to be 0 as well, so the CO2 has to become immobile. And therefore, you get the value of S* just being the immobile amount corresponding to this initial one. And then if you look at the flux functions, the scanning curves, and so essentially what you have is a Riemann problem. You can understand that in terms of a Riemann problem. And so the solution is a shock that perhaps I can explain it in this picture, which is the saturation flux plane. So the horizontal line is saturation, and the vertical is the flux of water. So this is during the CO2 injection. So when you start injecting, the saturation goes to 0.6. And then you have a Riemann problem. Essentially, you solve it, and it gives rise to this standard Buckley-Leverett wave, which is this dark line here. There is an inflection point there, so there is a tiny shock moving ahead. And then when you switch to a brine injection, now you're doing imbibition, so the scanning curves play a role. So this is the initial saturation that was constructed or created at the inlet during the CO2 injection. So when you inject water, then this shock, this dashed line is the shock that connects this saturation ahead or downstream, the shock, to that saturation upstream. So it's connecting the endpoints of a scanning line. And the slope of this line is the speed of the shock. And then the shock starts propagating and interacting with this rarefaction. And as it does, it speeds up because from the measurements, the slopes of the scannings are becoming steeper and steeper and steeper. So this shock speeds up. And as it moves across, it leaves behind a mixture of immobile CO2. So this line on top here consists of CO2 at immobile saturation. So everything is immobile here. And eventually this shock sweeps across the whole plume, and then everything is mobilized. This is the dramatic picture of how the shock speed increases. And again, this is because of the scanning curves are becoming steeper and steeper as we move to higher and higher saturations of water. So the slopes of the scannings are becoming very steeper as we move to close to water saturation 1. And so this is this one-dimensional simulation which describes exactly what I tried to say. The horizontal line is the porous medium, so gravity again points in that direction. The arrowheads here indicate the location of the injection, so the injection takes place at this location 1. And this black arrow here is because we are assuming that there is this background flow coming from that direction. So the white arrowheads are during the CO2 injection, and the black one is during the water injection. So the solid line is the saturation of water, and you see a typical Buckley-Leverett profile here, rarefaction and a shock. And the dashed line is just the flux of water, and we displayed it there just to visualize or to facilitate the location of the trapping shock, because it's hard to see it from this picture. So when the flux of CO2 is 0, so there is ahead of the plume, there is no CO2, so the flux is 0. But in this location here, for instance, there is already some CO2, but you see that the flux here is 0. It's because the CO2 has become immobile. So this plot here is actually, we have zoomed in. I mean, in the horizontal scale, we have blown it up by a factor of 100, I guess. I forget how. Just so that we could see the shock. And you see the trapping shock here. And exactly at the location of the back of this flux pulse of CO2 that indicates where the flux is 0, and therefore the CO2 is immobile. So you see the trapping shock there. So the CO2 ahead of it is mobile, but what is left behind is totally immobile. Okay. So Oh, I see. All right. Okay. All right. All right. So then So that's it then. So one other thing that we try to do is to sort of, it's a very simple and unsophisticated analysis of the possible cost of this process, because you inject in CO2 and then after that you inject water to speed up this immobilization as a residual phase. So we looked at the volume as a way of a sort of a simple way to quantify the cost of this process is to look at the volume of brine which is necessary to immobilize a certain volume of CO2. So and it turns out that in this one-dimensional scenario, and one is perfectly proportional to the other one. So in other words, the volume of brine is directly proportional to the necessary to immobilize the CO2 to the volume of CO2. And it is given by the slope of this line here. Here on this vertical axis we have the volume of brine, and here the volume of CO2. And the slope gives you this ratio, what is the volume of brine necessary to immobilize a certain volume of CO2. It turns out that this depends on the injection rate, because the injection rate affects the profile of the CO2 during the injection of CO2. And so, for instance, in this case, it's essentially a 0.1. So you need 10%, 0.1 volume of brine to immobilize one volume of CO2. And this is a function of as I said, of the injection rate. So what we have here on this side is the volumetric overhead, which is this ratio here. We're calling it volumetric overhead as a function of the injection rate. And it increases as the injection rate increases, and it levels off. So from this point of view, it would be sort of advantageous to inject at very low rates, so that you need less water or brine to immobilize CO2. But on the other hand, when you inject at a lower rate, the plume extends spatially to a much larger region, because you're forcing just a small decrease in the saturation of brine just ahead of the inlet. So then there is sort of this competition. If you inject at a high rate, you need more water to immobilize, but on the other hand, the plume will be essentially immobilized around the well, the injection well, so it does not propagate too far away before being immobilized. So let me just summarize what we did was the main conclusion is that at least in this simple scenario that we looked at, the CO2 trapping is caused by this fast-moving shock that is formed as soon as you switch the injection of CO2 to injection of water. And even if you don't inject water, if you simply stop injecting CO2, there is some background flow, so this process again will happen. Just that if you inject water, you speed it up. But if the shock forms and it propagates very fast and immobilizes the CO2. In this idealized scenario, all the CO2 is immobilized. But we made several simplifications there. And perhaps one thing that we should really look at is the effect of compressibility. The shock speed will definitely decrease, but perhaps it will still be an effective way of immobilizing CO2. And just to mention that even though we did this in one-dimensional, if you do in a radial flow, the same analysis applies. You just have to change the similarity variables, and the conclusions are essentially the same. So the effect of geometry is simply that as as the waves propagate, they slow down, but the same trapping will occur. And with that, I thank you for your attention.
Yeah, we have small time for discussion. Pacelli, you want to ask?